Okay, here is a projectile motion problem. I gave this as a quiz, and so I'm just also solving it for you so that everyone can have an answer. Maybe you got this quiz correctly. It doesn't really matter. I think it's still fun to solve it. And I'm actually going to do this two ways. Analytically, numerically. And I left off the y. Okay. And I think it's useful to do it both ways. It's pretty straightforward. So let's think about this problem. If I launch a ball off of here, then once it's in the air, there's only one force acting on it, and that's the gravitational force. If I use the momentum principle, then I get this. F net equals mg equals ma. So that means that the acceleration vector is g. Now, g is the vector 0, negative 9.8, 0 meters per second squared on the surface of the Earth. That's a g. So I know the acceleration. Now, I'm not going to derive the kinematic equations. I'm going to write down the kinematic equations because there's really just one kinematic equation that I need. If I represent the position of this with the vector r, then I can say, and it starts right here at r0, and it ends over here at, let's say, r2. I guess call it r1 and r2, doesn't really matter. Then I can write the following. r2 equals r1, 0, plus v0t, delta t, technically should be delta t, minus 1/2 g delta t squared. So this is my only kinematic equation that I need, but it's a vector kinematic equation. So this is the vector position at the end is equal to the vector position at the beginning, plus the vector initial velocity times the time interval, which I don't know, minus 1/2 times the acceleration, which is g. No, I'm sorry, it's plus g, because g, I've already have a y component is negative 9.8, but this is the acceleration is g. That was my mistake, t squared. Okay, so all I need to do is solve this problem, and I know the initial conditions, right? Because I know the initial position, this is launched off a cliff, and so the initial height is 4 meters. The initial velocity is 11 meters per second at 33-degree angle, which is weird, but that's the way it's usually given. And then I gave the mass too, because I'm going to do it a slightly different way. And so I just need to find out where it lands over here. If I knew the time, then I could use the time to find the final position and get the final x direction. But I do know something about the final position. I know the final position r2 is going to be equal to the vector x, 0, 0. I'm going to call this my origin. And then I don't know my final x value, but I know my final y value. I know my initial position is going to be equal to x is 0, y is h, which is 4, 0. I can write it like that. What about the velocity? Do I know the velocity? Yes, I do. The velocity, the initial velocity, is going to be v0 times the vector cosine theta sine theta 0. So if I draw that velocity vector right here, there's my angle theta. This is a magnitude of v0. The horizontal component is down here. That's going to be v0 cosine theta. The vertical component is right there, v0 sine theta. So I can write that as a vector. So I know r2, kind of. I don't know x value. I know r0. I know v0 and everything. So really, the only thing I don't know is that. And time. So there's two things I don't know. So it actually, since I have these I could write this all out as variables, but I don't want to. Instead, I'm going to write this as two equations. I'm going to write this as an x equation, which will just be x2 equals x0 plus v0x delta t plus 1/2 gx delta t, and I know that looks weird. So in this case, gx is the x component of the acceleration, and that's 0. x0 is 0. v0x is this, v0 cosine theta. So I know that. So I can write x2 equals v0 cosine theta delta t. So if I know delta t, I got x2. That's it. The other equation I can write is the y version of this equation. It looks like this. y2 equals y0 plus v0y, yeah, delta t plus 1/2 gy delta t squared. So let me just simplify this. Y2 is the final y position, that's 0. The initial y position is h. The initial y velocity is going to be plus v0 sine theta delta t. And then the y component of the acceleration is negative 9.8. We call that negative g. 1/2 g delta t squared. I can actually solve this equation for t, because the only thing I don't know is delta t. So let's do that. So let me write my equation again. So I have 0 equals h minus or plus v0 sine theta delta t minus 1/2 g delta t squared. And I'm going to replace this with just t, because if I say it starts at t equals 0, then delta t is t minus 0 equals t. So now I have 0 equals h plus v0 sine theta t minus 1/2 g t squared. And I have a t squared, and a constant term, so that means that I have to use the quadratic equation to solve this. So that means that t is going to be negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. I got that right? Yeah, that's right. So that's going to be, in this case, this is a, that's b, and that's c. So negative b is going to be this, negative v0 sine theta, not the t, plus or minus the square root of b squared, v0 squared, sine squared theta, that's right, minus 4 times a, which is that, so it's going to be plus 2g, c is that, h, all of that divided by 2a, which is negative g, because I multiplied it by 2. Okay, so let's put in my numbers. G is negative v0, so it's going to be negative 11 sine 33 plus or minus, I'm going to get two answers, the square root of 11 squared sine squared 33 plus 2 times 9.8 times 4, all of that over negative 9.8. I think that's right. Okay. Let's just take the, I don't know which one's going to be the, I'm just going to do the plus. So t plus. I'm going to do this on my dumb calculator, which I hate these things. Okay, let's just see if I can do this. So I'm going to put parentheses, negative 11 times sine of 33, I am in degrees, plus square root. Can you see this? Plus square root, there it is, square root of 11 squared times sine of 33 squared. That looks weird, but that's the way you do it. Oh wait, what the heck? Sine of 33. How'd I go back one? Sine 33 squared. I think that's right. Plus 2 times 9.8 times 4, close parentheses, divided by negative 9.8, enter. Error. Crud. Okay. I'm going to do this in Python. Because I just don't like typing all that stuff in the equation. I wonder if I did a square root of a negative sign there. Let me just do this part right here. I don't want to give up completely. So let's say negative 11 sine 33 plus or minus this number. So I'm going to say square root 11 squared times, I'm going to put it like this, sine 33 parentheses squared, I'm not sure that's what you have to do, plus 2 times 9.8 times 4, close parentheses, enter. Okay, so this is 10.691. All of that over negative 9.8. Okay, let me give that number. Clear. 11 times sine of 33. 33. And this is 5.99. So you see right here that if I include this as a negative and I add it to this, then I'm going to get a positive number. But then I'm going to divide by a negative number. So that means I want to use the negative. So that's all I want a positive time. So I'm going to do this minus 10.691 equals, and that divided by negative 9.8, enter. Okay, so I get 0.4796 seconds. That was stupid. I feel dumb. Okay, now I can go put this back in my x equation, and I get x2 equals v0 cosine 33 times that time of 0.4796 seconds. And let's do that. I get 11 times cosine 33 times 0.04796, enter. And I get 4.4. That can't be right. Clear. Okay, let's say 11 times 0.4796 times cosine, 33. Huh. I know that's not the right answer. Okay, well, I made a mistake somewhere. You know what? I'm going to proceed, and then I'll fix this. Okay. Let's go do this same thing in Python because it's a little bit easier. So here I am in GlowScript v Python. I'm going to give you the code here. I'm not going to make a graph. I'm not going to make a animation. I'm just going to get the value. So let's start. I'm going to write my vector equation. I'm going to say r equals vector. Let's put my values up here. v0 equals 11. Theta equals 33 times pi divided by 180. I want it in radians. H equals 4. G equals vector 0, negative 9.8, 0. T equals 0. Let's see what else. Oh, I'm going to mass. The mass equals 0.1. Okay, I actually gave them the mass. I wanted them to do this with the momentum principle, but we're just going to use acceleration. And so I'm going to go ahead and do a numerical calculation. If you haven't seen this before, that's fine. And this looks like it's cheating, but it's not. So I don't even need the mass. So let's just say dt. I do need a time step. The thing I'm going to do here is break the problem into small time steps. During each time step, I'm going to assume that the acceleration is constant, which it is. And I'm going to assume that the velocity is constant, which it's not. But if it's a small time step, it's kind of close. Okay, so then I can recalculate my new position and just have a whole bunch of time intervals. Okay, I need, let's say r is my initial position. It's going to be vector 0, h, 0. And now I'm going to do this. Let's say v equals vector, it's going to be v0 times the vector cosine theta sine theta 0. Now I can do my loop. While I'm going to do this. While r dot y is greater than 0. So I'm going to keep running this until the y position of r is at 0. And the first thing I'm going to do is to update the velocity. So I'm going to say velocity equals velocity plus g times dt. Not t, dt. Okay. And g is a vector, has a negative y component. I don't put negative g. G is a vector. Now I'm going to use that to update the position. R equals R plus V times dt. And now I'm going to update time. T equals T plus dt. That's it. All I need to do, once it's done, it'll be at y equals 0, and I can print the position. Print r equals r meters. And let's run it. And there you go. Let's print out the time, because I got a time of 0.4 seconds, and that's just seems weird. T equals t seconds. And I made a mistake in my other calculation. Let's see if we can fix that. Okay, let's do that the simple way. I don't want to leave things in a bad situation. Okay, so I'm pretty sure I had my kinematic equation correct. So I had I'm going to write this. A equals negative 0.5 times g dot y. That was my A value. And it's a number now, right? Because g dot y is negative 9.8. That's a number. A is a number. B is a number. It is equal to v0 times sine of theta. It's just a number. And then c is this number equal to h. So now I can do this. T1 is going to be equal to negative b plus square root of b squared minus 4 times a times c, all of that divided by 2 times a. And then I can do the same thing for T2. It's going to be the exact same thing. And this is why Python's a better calculator than your calculator. And all let's do is change that to a minus. And let's print T1 and T2. Print T equals T1, T2 seconds. And something bad happened. Did I get the quadratic equation wrong? B squared, it's negative b plus or minus square root of b squared over 4. B squared, not a number. I did get an error. Okay, let's see. What did I do? Let's just double check. Quadratic equation. I must have a minus sign in there wrong. A squared plus b c. I feel dumb looking this up, but sometimes you just forget things. Quadratic formula, that's what it's called. Quadratic formula. Negative b plus or minus b squared over 4ac. What the heck did I do wrong? Negative b plus square root of b squared minus 4ac over 2a. B is v0 sine theta. A is, oh, that's right. That's the problem. A is not negative. Okay, got it. Okay, so there's my t. There's my I get the same t's. I was getting the. That's weird. Okay, I had the negative. I just got the whole thing backwards. I was pretty close. Okay, and then I can say x equals v0 times cosine theta times t2. And then that's fine. Okay. So I was pretty close. Got the same thing. Okay. There you go. Code down below. Nothing else to say. Hope that helps.